Okay, thank you. So thank you very much. First of all, I would like to thank the organizers for giving me the opportunity to present my research work. Today, I'll be talking about in search of the new shock tracers in the low velocity shock region of the interstellar medium. So the interstellar medium is dusty, icy, and chemically rich. And just now we have heard from Alexandra that there are several mechanisms by which the dust molecules in the interstellar mediums, they are forming. And for example, they are forming during the stellar evolution at the less AGB phase, the carbon restart, they throws the materials in the interstellar medium, and that is the dust. Finally, they form different type of molecules. And what another part I will be talking today after Alexandra is this, that how the shock wave can use or can change the chemistry in the interstellar medium. So the evolution of the dust in the ISM is a very interesting area of research, and there are several studies have been done on the thermal processing of dust. However, how the shock waves actually process the dust in the ISM, that has not been explored very well. So what we wanted to know is what happens to the carbonaceous materials which are forming in the outflows of AGB stars in the ISM when they are exposed to the shock wave. So when it comes about the shock waves, as we all know that shock in the astrophysical environment, shock waves are omnipresent, and it forms by various processes like the stellar star formation through the jets and bipolar outflows, evolution during the stellar via the stellar winds, and the death of the stars, which is nothing but the supernova explosions. And when the shock wave is generating in the interstellar medium, they strongly affect the dust evolution. And the evolution, and we all know that dust plays an important role, as they are acting as a chemical agent, they are acting as a dynamical agent, that is the dust couples with the magnetic field to the gas, and also a physical agent, that is the source of heat in the post-shock gas. So in order to study this effect of the shock wave on the interstellar dust, we have this shock tube facility at the Indian Institute of Science, Bangalore, where we have a shock tube of like 8-meter length. And this shock tube is separated in two sections. One is the driver section, as you can see on the left, and another is the driven section on the right. And this tube, the length of the tube is roughly around 7 to 8 meters approximately, and the diameter of the tube is around 80 mm. And we can go with this shock wave. So this is actually a pressure driven shock wave. So what we do, we put the driver gas so here, and in these two sections are separated by an aluminum diaphragm. When the diaphragm bursts, it creates the shock wave. And when it creates the shock wave, within a few milliseconds, the temperature can go like around like 8,000 Kelvin. And what we want to see at that temperature what happens, or how these molecules, the dust molecules, are getting processed. So, so the basics of the shock tube. So just in a small slide, I tell you that here there are the two sections, the driver section and the driven section. So this is just one, and this is the pressure. So the moment shock wave is generated by rupturing the diaphragm, so that's the P2. So this is the P2 part, which is the incident shock profile. So right hand side, I'm showing the monochromata trace, which is connected to the shock tube with the pressure transducers. And at the same time, when the shock wave is creating, at the same time, on the other side, the expansion wave goes. So the shock wave direction is towards this side, and the expansion wave towards the opposite side. And then at some point, the shock wave goes and comes back, and that is reflected shock wave. And when it's the reflected shock wave, the pressure increases like around 30 bar, and that time the temperature can go, as I mentioned in my previous slide, around 5,000 to maximum 8,000 Kelvin we can reach in this process. So the first target we chose to work on C60, because as we all know, C60 is omnipresent in the interstellar medium in various sources. It has been discovered. And there are several studies have been done about the photophysics of the of C60 in the ISM. What we want to find, is there any link between the pH and C60 in the ISM in presence of or induced by the shock wave. So in order to do that, what we have done, we have taken C60. I'll briefly explain the experimental setup here. So we put the C60 microcrystal here in a plate, and this is the sample chamber. So you can see this sample chamber here. And then once the shock wave creates, it interacts with the C60 compound. And when the incident wave mixes a small quantity of the shock wave and deposited on a plate, and which is the argon bath, and behind the reflected shock wave, this particle temperature when reaches up to like gas temperature and leads to the sublimation of C60. And then thermalization occurs within hundreds of microseconds. And then, so what we initially did to study the ex situ chemical analysis of shock-induced C60 in presence of hydrogen. So Ludovic did this experiment where he has exposed C60 in presence of small amount of hydrogen. And after the experiment was over, we collected the residue, and the residue was analyzed using infrared microscopy in Soleil. And as you can see, from hydrogen here, that the lowest one is the hydrogen concentration is the minimal, so H equals 0. And then we are increasing the concentration of hydrogen from 1.4 up to 5.5 millimolar, like that way. So as we can see, if we increase the concentration of hydrogen, we started to observe various CH containing species. So that is something is very interesting to study now at this point. Like we can see there are several CH containing molecules are forming. So we wanted to see, can it be possible that C60 upon exposure of the shock wave, can it go in presence of hydrogen? Because as we know, hydrogen is also there in the interstellar medium, is widely available. So can it form the pH molecule? So we go in the other way. So we have also studied the phase diagram of C60. If you see the phase diagram of C60, so the region of the interest of our experiment is around like a little more than like 1,500. So in this particular experiment, what I have shown, so that the temperature and the pressure, which tells us the molecule is the C60 crystal. So we have done the XRD analysis of the C60 microcrystal, as you can see. When it is at the microcrystal stage, so it is pretty sharp peaks. And when we expose the C60 with hydrogen, it's becoming more amorphous in nature. And this data is also supported by the Raman analysis, where we can see upon exposing with the shock wave at different temperature, the C60 is showing these graphite-like signatures. So graphite G bands are coming. So it tells us that C60 surface, C60 molecule is probably getting ruptured, and it is forming more like a graphite-like structure. So then in one step forward, I started to work on the in situ chemical analysis of the shock-induced C60. So in this process, what we did, instead of collecting the sample at the end, we also thought of putting an optical flange, and this optical flange was connected to multiple spectrometers and a monochromator. So I will explain you the reason for the spectrometer was we wanted to see what happens to the visible region, if there is any signature species is forming. And also we wanted to see how the spectral profile changes over time. So for that, this monochromator was put. So here, as you can see in the zoomed image, so this is our optical flange, and these orange cables, these are connected to our small STS UV spectrometer. So what we observed when the shock wave exposed and finally after the experiment, I mean, when the shock wave created and it interacted with the sample, in our spectrometer, we recorded this spectrum. And we know that this spectrum, so we have integrated, and this spectrum is an integrated emission spectrum. And this emission spectrum is well-known signature of C2, SWAN bands. And we did not observe any C3 fragmentation though. And then we realized that this could be because that when C60 is exposed to shock wave, it's forming C58 and C2, and then C58 is going like C56 and go on like this way. So at the same time, we also observed there is a broad component. So we wanted to understand what is actually the reason behind what is broad component. So in order to do that, we had to do theoretical simulation. So this is the, I will tell you what the theoretical simulation we have done. Now, when you expose C60, so this is the probable shock-induced decomposition scheme. So as you can see, C60 is forming C58 plus C2 excited, and this C2 excited is forming C2 plus, radiative emission. So like that way, C58, like in the finally, it goes like C8, C2, like this way it's going on. So all this tells us that C2 is forming probably via this mechanism. So in order to understand, as I told you, we have to we also did the theoretical simulation. So for that, we use the exocross package to simulate the absorption cross section of C2 at various temperature. So for that, we took the list of transitions and the partition function of C2 radical from Euschen-Poetel, and the C2 spectrum was simulated from 4,000 up to 7,500 Kelvin. And the pressure dependence of the simulation was considered using the void profile. And then we realized that in this medium, as you have seen in my slide, where I showed the monochromator trace, it is the trace of coming from the instrument. So we have seen that we also found that there is a huge concentration. The concentration of the molecule is optically thick medium, and in this optically thick medium, the absorption spectra are actually affected by the self-absorption phenomenon. And in the self-absorption phenomenon, there are two parts. One is self-absorbed C2 emission, and another is the object emission, which can be represented like this. So overall, if you see the total flux is nothing but the sum of these two. So we need to consider the effect of self-absorption in the simulated spectrum. Where you can see in this spectrum is also this tau, which is nothing but the concentration, which is transmittance, and this transmittance is related to the concentration. So definitely the concentration is going to play a key role in this experiment. And that is what we have found, as I will show you here, that we have taken the absorption cross-section calculated by exocross, and then we have corrected the spectrum using self-absorption phenomenon with a concentration of 1.4 10 to 16 cubic centimeter. And these are the different temperature, as you can see, starting from 4,500 up to 6,000. So this is the spectrum of C2. And the moment I am increasing the concentration, you can see the change in spectrum. So it is becoming more thick and the broad spectrum is happening. And here it is even worse. And then at 7 micron, at 7 in 10 to 16, this concentration is pretty high. You can see how much the spectra has been changed due to the self-absorption effect. And at the same time, as you can see in that equation, there is, apart from the concentration term, which is related to the tau, there is also the emissivity. So we also did the changes in the emissivity, and we have seen that this is the concentration when 2 into 10 to 16 cubic centimeter at temperature at 5,000 Kelvin. We see we have changed we fixed these two, and then we changed the emissivity, and we see this is the spectra is getting changed like this way. And then finally, this is the one what we compare with experiment and theory. So as you can see, the colored or the spectrum is the experimental spectrum, and this is, and the black one is the theoretically simulated spectrum corrected by auto-absorption effect or self-absorption effect. So as you can see here, we also calculated, so the concentration, as I told you before, the concentration is 2 into 10 to 16 cubic centimeter, which is around 8% conversion. So we calculated that. So we see that the amount of C60 is converted to C2. It's around 8% is coming. And the nature of this broad component, we are still trying to understand. It's because of the particles or the carbon clusters. So in order to understand that, our collaborator Odd Simo, we have done the simulation. So Odd did this simulation with a with the box, the molecular dynamics simulation with a box of 60 angstrom wall at 2 different temperature, and the molecular dynamics simulation with the DFT tight binding potential with the Dimon nanopore. And this, as I told, the repulsive wall was included, and the simulation with the random velocities are run and the fragment distributions are analyzed as a function of time. And the decomposition we can see the starts above 3500 Kelvin for times 4 nanosecond in the experiment in the millisecond scale, and we see the fragment above 2500 Kelvin. And at 5000 Kelvin, only clusters which of carbon size less than 14 remain. And the combined emission of these numerous isomers are possibly responsible for the black body emission. So we are also working with Ozan Lachinwala. So you can, he will be speaking next to me also on the about how one can use this type of simulation to calculate the these various molecules, what are the effects of on that. And then, so let's come to the summary and the perspective. So the first, so this is the first application of the shock tubes to the laboratory astrophysics, and it's a new tool to the community. And this is a complementary expertise where we combine experimental, physical, and chemical analysis and theory. And also our aim to contribute to study the dust cycle and identify new shock tracers. So for example, the key question we are asking from this work is that can it be like C2 is shock tracers? Because this we are also trying to understand, because we don't know, we know C2 has been identified in the interstellar medium by their Phillips band probably, but whether it has been, it could be a potential shock tracers, this is still not known. So we are working on it right now. So in the perspective, we next thing is to understand the time resolved emission profile of C2, and also study with various type of interstellar dust, starting from hydrogenated amorphous carbon, PHS, graphene silicates, and also the multi-species broadband spectral monitoring with using gravity-based spectroscopy. And as I told you that we have also worked, I mean, we are right now working on to understand the time resolved profile. So for that, we have built this setup, and in this multi-species monitoring through the visible emission spectrum and development of new transportable instrument associated with a grating and a spinning meter and a CMOS camera, which can give us a more detailed time resolved emission profile of a particular emission band. And with this, I would like to acknowledge my colleagues in France and my colleagues in India. And I'd like to thank all our financial support from CEFIPRA, PNP, SPN, and University Rennes 1, IPR, Indian Institute of Science, PCMI. And I would like to finally thank you for your attention.